So notice the graph that we're looking at. One big thing, once I look at a graph, I'm noticing we have one arrow. I'm going to annotate that right now, just so I know that we have an arrow here. The first question that is asked is this relation a function? If you want to test whether or not something is a function, you use the vertical line test. And I'm sure you guys have all done the vertical line test before. In order to use the vertical line test, what you do, I think this is going to work for me, is you take a vertical line. I'm going to use this piece of thread because it's very thin. And you essentially are moving over the graph with a vertical line and seeing if there is an intersection with the graph more than one time. You'll notice here that at every location in the graph, even at this jump, we still only touch the graph one time. Because we have an open circle and a closed circle, right, it's really only one location. And even down here where the arrow is. This passes the vertical line test, so yes, it is a function. The next question is the function one-to-one? When something, if we're testing for one-to-one, you're going to be using the horizontal line test. In fact, I'm going to zoom in a little bit. See if I can spell horizontal right. The horizontal line test, which is very similar to the vertical line test, but well, as you guessed it, we use a horizontal line. If you look here, you'll notice at this location, our graph intersects my horizontal line 2 times. In fact, it does it a lot, right? In fact, it's intersecting it twice here, twice here, twice here, 3 times right here, 2 times, 2 times. If it intersects more than 1 time using a horizontal line, it is not on 2. So this function is not on 2. And honestly, once we get out of this section, you probably will not see the word on to very frequently until you start to get into higher up math. Now, will the inverse of this relation be a function? If you want to test whether or not the inverse is a function, you also use the horizontal line test. We also use the horizontal line test. In fact, I can squeeze test in right here. Boom. So if we go to test, I'm going to do it again just because I'm showing you guys. Notice here, it fails the horizontal line test, right? Boom. We're intersecting more than 1 time. If it fails the horizontal line test, the inverse is not the inverse is not a function. And I'm going to put in parentheses here, horizontal line test. Boom. So we've covered questions 1 and 2. The next question says, write out the domain and range in interval notation. So again, I'm just going to go through this with you guys. We'll have an opportunity to practice some of this in a little bit. For domain, remember, we're looking left and right. This arrow, though it is telling me we are going down, it's also telling me that we continue going this way. In fact, I like drawing this out because it really illustrates that our line continues moving. So when I'm looking at the domain here, let me get a fun colored pen. Domain, when I look to see how far left we go, notice we keep going to the left. I know for my domain, because of this arrow, the furthest left I can go is negative infinity. Would anyone like to type into the chat how far we end up going to the right? When we look to see how far right we go, I saw, Antoine, you said -1. That's how far this section goes, right? So you're not technically incorrect. But the thing is, after it goes by -1, it starts right back up on this second portion. So this graph continues to go to the right. Even though this segment stops, it starts right back down here. So it continues till we get to +9. And we are inclusive because we have a full circle there. I know that tricky portion is where this breaks up, but remember, if it just stops here, it kind of just fills in the circle and we start right back up. Yeah, I know it's kind of a tricky example, Antoine, but that's why I picked this one to go over with you. Let's look at range. Right? The lowest value. Right? If we're looking at the lowest value, I think we can see from this arrow that we're going to keep going downward. So that means we are starting at the lowest value, negative infinity, and we keep going up, right? We're going to keep going up, keep going up. Notice I have graph over here, keep going up. I should have did this in a different color in hindsight, and we're going to keep going up till we reach +4. Now at +4, are we going to have a empty circle or a full circle? Very nice. I'm seeing it, guys. It is a full circle, right? Because remember, we would clearly mark empty circle. So this goes all the way up to 4, inclusive of 4. We have determined our domain and range. All right, now I definitely got to switch colors up. I should have took some highlights. I definitely brought some highlighters home from work. I just got to remember where I put them. So now that we're checking this out, the next question says identify intervals over which the relation is positive. So though we didn't really go into depth as what it means for a relation to be positive, when a relationship is positive, it means it's above the x-axis. Which makes sense because that's when its outputs are positive, right? We know that above the x-axis is positive, right? Above x-axis. It appears as though our function is above the x-axis only during this section. Here we have positive, and in fact I'll even mark negative even though it's not asked for us here. Oh, is that the exact same? I chose. That's a. No, those aren't the same color. Are they the same color? I'm colorblind if you guys didn't know that. But all this. Thank you. They look exactly the same to me. Maybe one's red and one's fuchsia. Very close. Thank you. So you can see here, these sections below the x-axis are negative, above is positive. So our interval, and now for the interval, you can choose if you want to use inclusive or exclusive. I'm choosing to use not include those points. It's from 2 to 8. The reason why I'm choosing not to include them is technically at 2 it is 0, so it's not positive, and technically at 8 it is 0, so it is also not positive. That's why most people tend to use this, even though you may see inclusive brackets here. last section, is we need to identify all x-intercepts and y-intercepts. So we're going to start with the x-intercepts. Do I have a nice, I think I have a black marker which would really stand out right here. There it is. Boom, black marker. If I'm looking for x-intercepts, I'm looking for where my graph crosses the x-axis. When I see that, I think these two are our only two x-intercepts. So our x-intercepts are going to be 2, 0, and 8, 0. For our y-intercepts, I wish I could see this a little better. It looks like it's crossing right here. And I'm going to kind of draw a little line up here. To me, that looks like, we'll say 1.5. Is everyone cool with calling that 1.5? Because it's not, it's between -1 and -2. I think we could say it's going to be an approximation, but I think that's a safe one to bet. Now, for the inverse. To determine the x and y intercepts of the inverse, which we cannot see, right? This is not the inverse. This is the original function. What we're going to be doing is you just switch these two. So our x-intercept, the only thing that changes is its location, right? When you do an inverse, or when you're working with an inverse, Lewis, get out of here. Lewis, I am recording this, and you know that for our x-intercept, like I said, -1.50. And then for our y-intercepts, it becomes 0, 2, and 0, 8. Remember, guys, one of the key things about inverses is if you're going from an original function f of x to its inverse, which we write out as, you're switching x and y. That's one of the key features of an inverse. And again, we haven't talked much about that, but that's something that you've covered in your Algebra 2 class, Algebra 1 class. So this covers example 1 for try it.